on Stabilized Wilson, and yeah, I'm working with these guys. Okay, so yeah, so far many people introduced the background, so I want to. Actually, I didn't prepare much about the introduction, so yeah, we here we just compute the theta some contribution to the neutron nEDM. Okay, so first this is the QCD Lagrangian in Minkowski space, and there is a theta bar term here, and yeah, of course theta bar is very small, so we can do like this linear assumption. And topological charge is defined in standard way like this. And here T is flow time. So we use the gradient flow. And yeah, and we study the vector form factor with inserting topological charge. Okay, this is the previous result by Jack and Andrea Schindler. And so actually, yeah, this is not this work, but yeah. So this point, their simulation point was here and here and here. So it's a little bit far from the physical pion mass. So there was some difficulty. So here we exactly redo this calculation on stabilized Wilson fermions. So, but we are still preparing the configuration. So in this talk, I will just show the results only at the 400 MeV pion mass and 3 different lattice spacing. So we can do the continuum extrapolation, but we cannot do the pion chiral extrapolation. Okay, so we use these 3 ensembles. So coarse lattice, fine, and ultrafine lattice with 3 different lattice spacing, and pion mass is almost same. It's 400 MeV, and lattice volumes are all different. And for C4 and F4, we have almost 1,000 configurations. But for the U4, now we have 5 or roughly 600 configurations. But in this talk, I measured only for 200 configurations. And also we use roughly 100 stochastic source locations to improve the statistics. Okay, also we did the scale setting using the standard way, using the gradient flow written in Lucia's paper. So yeah, we determined T0 from this definition, and yeah, for 3 ensembles, yeah, we determined T0 very precisely. Okay, so now first we compute the nucleon mixing angle alpha n, and yeah, the G2 is just nucleon 2-point function, and G2Q is 2-point function with inserting the topological charge here. So their ratio will give the nucleon mixing angle, and here P hat is some projector, and for the 2-point for the denominator, we choose this unpolarized projector, and for the numerator, we here I show the result for 3 projectors. So the blue is gamma 5 pi plus, and yellow is gamma pi plus gamma 5, and green is just average of these two. So yeah, they are all consistent, and we use the green data for our analysis. So this is the autocorrelation study. So here I plot the error of alpha n versus bin size. So for C4, F4, and U4 ensembles, and if you see this, roughly bin size 20, the error saturated, and also for F4, it's saturated at bin size 20, and yeah, U4 we have only 200 configurations. So, and roughly, yeah, we choose 10 for the bin size for U4.
Understand where the direction of the error changes from one to the other. Like if the error is smaller,
maybe that is related to the autocorrelation between the measurements on that ensemble. So still,
the first one should increase indeed as well. Yeah, check that.
Yeah. But if the
I mean, you cannot increase the error if you increase the bin size.
Yes, okay, we will check it. Okay, so we also improved the alpha n using the same method as Jack did in our previous result. So only insert the topological charge at one time slice, and that is Q bar. And if we sum the Q bar for all time slice, then it becomes the topological charge. So if we just insert Q bar between the nucleon, then that's the delta 2 Q, and G2 bar Q is the symmetric summation of delta 2 from 0 in this case. So if we see two different projector for that, so blue is gamma 5 pi plus, so it's symmetric from at 0. So here blue bar is the sourcing separation of the nucleon. So from 0 to this sourcing separation, the signal, so there is a signal and also opposite direction, and the others are all 0 within the error. So it's just noise, and so we just take the summation window from 0 to sourcing separation, forward direction and backward direction. And for the yellow, the sourcing separation point is the symmetric, the starting point, and the summation window width is same, but starting from this. So it gives this is the accumulated accumulation plot. So as you can see, here is the summation window, and yeah, after that it gives the same results within the error. But here is the error is very small, and this is the error is very big. So we took this value for our simulation. So we compare. So we set the summation window to the nucleon sourcing separation X4, and here you can see we compare the unimproved and improved data. Error is much smaller than unimproved one. So here we also compared. So we extract alpha n from this plateau fitting and collect this result as a function of flow time t over t0. So yes, so if you see this blue and orange, the improved one is much better, and yeah, also same, also much better for the other ensembles. And this is the scale. So if you draw one the vertical line here, then all points are in same scale. So you can choose 3 points from the vertical line. So we choose actually the biggest slide value for U4. So we took these 3 values for this analysis. Okay, we also check the energy dispersion relation. So yeah, for 3 ensembles, we get the energy in this way, and these lines are not fitting function. It is just starting from this, and we use the continuum dispersion relation, and they agree with the data very well.
Yeah. Question: could you please repeat what improved stands for? What is the improvement here?
What is improvement? Yeah. So if you don't, yeah, unimproved is this data.
Okay.
Improved is this data.
Okay. So
they are agree within the error, but error is
okay,
here is much bigger and error is much smaller.
Okay.
Yeah. Okay. Also, yes, we compute jet B from vector word identity, and yeah, for 3 ensembles, and yeah, we multiply this renormalization vector to our vector current, so to renormalize that. And yeah, we also plot these 3 ZV values for 3 ensembles and try to fit with the one loop coefficient, and yeah, it works like this.
I guess that's a non-determinable point one.
Yeah, yeah, it's a perturbation theory. Yeah, this one.
This is A and B in the
Yeah, A and B. Yeah. Okay, so CPO, the electric dipole form factor, is F3 as function of the transfer momenta square and divided by 2 times nuclear mass. And in this limit, we can get the electric dipole moment and shift moment as a function of Q square. Okay, so now here G3 is defined. So there's 2 nucleon and current insertion and topological charge with a float. And the current is the for neutron. Yeah, like this.
That's the one.
This?
The charge are not the same.
There's 2 D. Yeah.
You're also counting the short wave for well, the 2D, but they have different contraptions. There's different contraptions. They're not just the same contraption. You know, the two neutron has one's parallel, the other one's crossover.
Mm-hmm.
So I think it's
Oh. Yeah. Very good. Yeah, maybe I found my mistake. Okay, so yeah, here also we define the ratio of 3-point and 2-point function, and also we multiplied some yeah, momentum this K factor to remove the nuclear time dependence. Okay. And yeah, also we use the fixed sink method. It means the momentum at the sink is 0. That means the momentum at the source is minus momentum transfer. Okay. So, and from the spectral decomposition, we can write the ratio as a function in this way. So there are so A is this, and here gamma tilde. There are two gamma tilde mu. That it has F1 and F2 tilde, and there is also F3 tilde. And from F3 tilde and F2 tilde, we combine it with the nuclear mixing angle alpha n, then we can compute F3. Okay. So also we improved the RQ using same technique. So insert the top project charge at only 1 time slice and add them symmetrically. So if you see this, yeah, so red is the sourcing separation and blue is the current insertion time slice. And yeah, after the sourcing separation, it's noise. And we just add this signal only in this window and also same length in backward. And the result is like this. So this value is the improved one, and this is the unimproved one. Okay, so we can compute F2 tilde and F3 tilde by dividing the coefficient from the RQ. Then we get F2 tilde and F3 tilde like this. For unimproved is blue and improved is yellow. So
what is the moment transfer?
I think this is Q square is 1.
Yeah, of course. Yeah. Do you have a plot for the moment transfer? Several.
Yes, sure. So first, we just compute. I just compute F2 and F3 by this, and yeah, from this plot, I extract the value by the plot fitting in this range, for example, for every momenta and every channel. Yeah. No, it's just
So have you tried doing like that?
done yet. Yeah. Okay, so this is the F3 divided by 2m as a function of momentum q square. So we did the linear fit for this, then we can obtain the dn and sn from this fitting. This is the result on the C4 ensemble. Okay, also, yeah, so we did the continuum limit for dn for 3 ensembles. And yeah, still we didn't do this current improvement. So here I show 2 plots. One is the linear fit in A square, and the other is A. And so to do this A square linear fit, actually we need current improvement. But yeah, it's a very preliminary result, and yeah, it gives non-zero value here, and the other fit gives 0 value. So definitely we need this current improvement.
Looking at the plot. So obviously correlated, it's not correlated, but it has to be, given how the band fits today, it's surprisingly small. Oh, never mind, I'm sorry, forget that.
Yeah. Okay. Okay, so also we did the continuum limit for shift moments. Okay, so yes, also there are two fits, and there is a chiral perturbations result, and actually this number is independent of the pion mass. So this value, so if we compare this value and our value, then they are agree within the error, and of course our result is non-zero.
Oh, you have a definition of S is finite.
Yes. So yeah, sign is also correct.
Actually, John, I don't understand your comment. G0 depends on the pi mass. G0 is proportional to pi squared.
Yes, but this value G0 divided by pi and pi square or something. There is a, so it's cancelled. Okay, so yes. Yes. So our ensembles are generated using some reweighting methods. So we need reweighting factor, but we didn't have a complete set of reweighting factor yet. So still it's coming. So so far our analysis is done without reweighting factor. And only we have the full set of reweighting factor for C4 ensemble. So I compare the final result with and without reweighting factor, and their difference less than 1%.
The Q-square error doesn't grow with Q-square. I mean, your error should be the same. Well, it's the same. Costs a large Q-square.
Yeah.
Usually the error goes up as also usually the form factors are larger.
Yeah, it's going to 0.
It's interesting. We don't see we hardly see any shift moment. It's very flat. Where's this at?
But the slope is consistent with what the type of peak.
Yeah, I understand.
And
The thing is that we see that to be very constant.
Okay. So yeah, let me conclude. So we compute neutron nEDM at 400 pion MeV pion mass, and yeah, to extrapolate to the physical pion mass, we need 200 and 300 MeV pion masses, and yeah, we are preparing that. And so maybe this is will be the full set of our ensemble. Still, we are generating the gauge configurations. So yeah, for the physical pion mass, we need this F2 and F3 and U3 ensemble. Yeah, and also we have to increase the statistics for the U4, and yeah, also we need to apply the reweighting factor for all ensembles.
oh yeah, that's true.
Actually, it might be worth investigating those like linear combinations of not just the neutron but a bunch that are designed like the electric three symmetric thingy from the break. So what,
So let's take the speaker again.
Yeah, thank you.
Sorry, I have to be, so Jangho's presentation was half an hour because I originally asked him to give a presentation half an hour, so yeah. It's my fault, so questions, please.
What is the dipole moment? What's the dipole moment that on this assemble? What is the DN value? Just want to like see the error bar.
It's yeah, 1.5 10 to the minus 2. If you believe the square extrapolation.
1.5. Oh, okay.
You would also have cam and data. Manual using those problems.
Andrea, can you take the microphone? What's the people?
Yeah.
I was thinking at the SU3 flavor symmetric point, you don't only have the pion loop, but you have the can and the eta loop. And that could impact your expectation for what the value would be.
The born people have a reaction before that. So we have like and
They do an expansion of. The way I said this is isosymmetric, and the Cal extrapolation is done keeping the trace of the core mass fixed. So
I mean, that bit of the results for SU3 in general. So then you can take the meaning of the mass of the K or the equal to the mass of the body.
okay,
Equal to the mass of the
yeah, but when so this is just the one value of the mass, and then when you go to chiral, the chiral gets heavier and the pion gets lighter. So here they are degenerate, but then towards the chiral limit they go towards the physical values there. So I guess one can still use the same formula. Obviously, so.
You have results for the proton?
Sorry?
Do you have results for the proton? Yeah.
Not yet. But yeah, if I change the current, the coefficient of current, then we can get it very easily.
Yeah, we are also the proper contractions for the proton. Yeah, we do. Yeah. This has been a marathon of Jangho to actually get these numbers on time for the workshop.
So what's next? I mean,
What's the next?
no, I mean, what are you planning to do after? I mean,
For break?
No.
no, I mean, how are you going to continue your work? I mean, what is the next plan? I mean, the next step.
Next step is, yes, we are measuring on this S4 ensemble. So we already have almost 1,000 configurations ready. So
Okay.
then we will have 400 ME pion ensemble points. And then, yeah, we still have to wait for these two and three,
Okay.
yeah, ensembles.
So you stay at the same pion.
So from my point of view, I first wanted to make sure the continuum limit that one of the repion is solid and robust.
Mhm.
That I get a signal, so the DDM is non-zero. Then the second step, I will try to recover it.
Okay.
Yeah, you go to the plot calculation.
Yeah.
You go to the calculation plot. But isn't there some market that's probably pretty small?
No, the DDM.
I mean, that's a that's a large. I mean, yeah, the continuum. I'm just saying it's very important because you're seeing 300% corrections in continuum, right? 0.004 to 0.0015.
Yeah.
That's really important.
There are also large errors. You take the first and the last point, they have to see much.
So yeah, so all of you is
With such a huge continuous extrapolation effect, to get the right answer, it's clearly very important to do the, yeah.
But we also have to do this because we want to constrain the EDM to be zero in the chiral limit. That's important to check this. I think the first thing we will do is to actually take the dimension 4 operator of the vector current and just change the coefficient to see what happens to the results. This we can do in analysis. to see if the color effects get affected or not.
Have you checked the sensitivity on the scale setting procedure? So have you tried to set the scale by use of some other operator? and see what
Yeah.
happens? Because
Yeah. As you can see, so after certain flow time, it doesn't change much.
I think more she's asking if instead of T0, maybe W, yeah.
there's a whatever.
Yeah, but we did not check that. Not yet.
Because that, I'm a bit surprised because you have these two values of prior mass that you declare to be very similar. And lattice spacing is not that large. So I'm surprised that you can really see a lattice sensitivity at the, you know what I mean? Because you say you have a 408 and 410 prior masses, as I see correctly. I would really like to see the full set of measurements on top of each other because I would be tempted to conclude that you have a zero lattice spacing effect there.
I don't get that. No.
Yeah, I mean, you have, these two C4 and F4 ensembles, and the lattice spacing is not too coarse. It's not too coarse. And you say you have similar values of prior masses. So suppose you make a scaling variance plot for a bunch of quantities. Do you really see a lattice spacing effect between these two ensembles? So my point is that there is zero lattice spacing effect there. And then you can't really extrapolate to the continuum, or you can really take this as a continuum estimate.
Sorry, my bad, I'm not following.
Yeah, I should.
The physical. This is kept fixed in physical units. So, and the point is to do the continuum limit on that line of constant physics.
Yeah, but what is the constant physics line? That's the point, because constant physics. Yeah, but how do you set that value? You see.
Of course, it depends on the scale, but I don't think it's going to change much. This is the scale setting for gradient flow. So it's the same, set the same TF and so on. That
TCR is fixed in physical. It's very precise. Can you show the values of TCR? Yeah. Those are the errors.
Very, very expensive.
Then the T0 is taken from the CMS, I think the physical T0.
For example,
But I mean, if you're not in the scale, I don't know, I don't. If you are not in the scaling, if you are in the scaling window, any other observable should give you the same. If you are not exactly in the scaling window, then you should have a scale sensitivity of these results, and that should be seen. I mean, I appreciate this very nice way of scale setting, but what something called like Edinburgh plot. Remember these things? No, okay, that doesn't. Okay, I'm sorry. We can check
we could try to change the way we fix the scale, and then and then redo the continuum limit. We could try to do that. Yeah.
And also, I'm just remembering when we did our scale setting, if we used the improved T0 and the omega baryon, we observed a flat continuum limit. I think this is what you're saying. Yeah.
That's exactly.
That's what you're asking for in not in physical units, but using the nuclear mass or something to set this. Yeah.
When you say improved, you mean removing color effects.
The T0, what I mean by improved is the work by Karen Holland and Fodor and Company, where they did the perturbative correction. Yeah.
We could do that too, yeah.
We already did that.
We actually did this for the chromogen. Questions from Zoom? Zoom people? Zoom people, do you have any questions? Sure, of course.
I have a very stupid question because I'm not an expert and I want to know more details about, the underlying details of the analysis. So you performed a continuum extrapolation, both assuming a linear term in A and a linear term in A square. But you do that because you wanted to check that the order A correction is large, or just because you are not sure about the leading order correction toward the continuum limit? So what's the reason?
So
Yeah, I mean, like these pictures here.
So yeah, I also show this result is very sensitive to the this what order A square improvement. Yeah, here. So to get the final results, essentially we need this order A square improvement. Otherwise, we will get 0.
Yeah, okay, so you expect to have order A corrections and you want to remove them because they are.
We cannot do an square extrapolation because we are not fully improving the correlation function. So we have improved. So CSW is not particularly improved, but the vector current is not. And so we, in order to be conservative, one would do extrapolation on the right hand side. But I've seen in the past cases where the improvement of the vector current does not play a major role. So if we want to be bold and see what happens if we don't do that, we will do the extrapolation in A square. That was just a bold exercise on the left.
If I recall, from some old work by Martin.
Some old work by Martin, Silas, and maybe Brian Taberzi and one of Martin's. I think even for unimproved Clover, they might have found with electromagnetic currents, you get A squared as the leading correction. I'll look that up.
Yeah. So we want to test this. We want to see. Also, the improvement depends on the current that we use. If we use the temporal current or the spatial coordinates, so the improvement term changes. And in one case does not contribute, in one case it does. And so we need to check. But in principle, to be conservative, we would plot the separation on the right hand side. But the hope is that once we fully improve the correlator, we will end up with a picture that looks like the left hand side.
So you know what was the physical origin of such corrections?
The order, yes, Jangho is written there. You see CV. CV is the improvement coefficient of the vector current, and so that's missing.
So my point would be, even if CV is not improved, it may be that the way it shows up in the baryon, it's only A squared.
There are cases when this happens. Yeah, that's right.
This error bar,
Maybe the fourth lattice spacing will help.
do you expect to observe, a better scaling if you also improve the topological charge?
So the charge is actually order A to the 4, 3-level improved. We use the construction of the charge, which contains rectangular pieces and 2 times 2 pieces, plaquettes. And that removes cutoff effect at 3-level up toward A to the 4, and then we flow it. And so we should check also in fact, one thing we should check, Jangho, is the scaling violations of the susceptibility. So this should be added in analysis. But in principle, that should scale like A squared because the theory is really fully improved. What's not improved here is the correlator. Yeah. That's actually one subset of the collaboration promise to do that. So we are hoping to actually constrain the continuum limit in that way. Yes, like Dina showed in her presentation. Yes, that's right.
So to make sure it's A square, you need an improved operator also, right?
Yeah,
So with the coefficients, so on. So yeah, right.
So
Okay.
that's the thing. This is a new lattice action, and when you change lattice action, you have to
Change that. Okay.
And so Jangho has calculated ZV. But we
Right.
calculate CV.
CV for the other coefficient.
We know how to do it, but yeah.
Okay, thanks.
Do you have the plot of the actual fit to the 3-point function? Yeah. Do you have multiple values of the sourcing separation time?
It's only one value of sourcing.
I
But
wouldn't.
We test. We compute only for 2 sourcing separations, and we choose the better. I choose the better one.
So I was just
Yeah,
gonna comment, I wouldn't be surprised if when you had another sourcing separation time, you did a one excited state fit, you'd see those numbers drift up to a sigma.
So, John, maybe I want to comment on this. What lattice is this?
I think it's C4 course.
So what's the time extent?
Time is
48?
9.
Hmm?
9 is separate.
No, the full lattice spacing, the full lattice,
96.
48, 96.
Yeah, 96.
Okay. So, but the sourcing separation here is 18.
No, maybe then it's U4.
Yes.
Yeah.
Yeah. So 18, right? So this is a very, it's already substantial. Like, so the plots we have seen during they start from 6, 7, 8. I mean, what in order to do the exercise, we should actually reduce the source simply. I wouldn't do that. I mean, that's, I mean, to go to even larger source inspiration, you will have lots of noise and it's not, I mean, rather than doing short source separation and trying to extrapolate, if I do it directly, a very large one, I think I'm not doing something.
So this, what's the last statement?
0.065.
We already choose the sourcing expression in physical unit 1.1 and 1.3. So two.
Yeah, that's
But
reasonable.
what I mean is,
For such a form factor.
but the problem is, get a contamination to the absolute normalization of the plateau from excited state. And since you clearly have excited state contamination, I wouldn't be surprised if it adds a little shift if you had a one state fit.
You
It'd be nice to see the other separation, to see what a.
you wouldn't say that's a plateau?
I don't trust plateaus at all. I can see
We-
the sign of the curves change. They change.
We will do that. We will do that analysis. But my comment is that the other presentation you've seen, the choice of the source inspiration is small, such to enhance that effect. There's a lot because the source separation we have seen are very short. Here, the source inspiration is actually it's 1 Fermi, more than 1 Fermi. Yeah. So. Yeah.
But can you also make a fit instead of
instead of just relying on the plateau, you make a fit with the constant, and then you double check that the constant is the same as the plateau, and then you take care of this worry.
But you need at least 2 extra sources of separation times to tease out the asymptotic value.
Why? I don't know, because I'm not familiar with this.
This is a fit. This is a constant fit.
No, I see that as a constant fit, but if you have a function and you add the constant, then you can really see if the constant equals to the asymptotics. It's not mathematically the same.
You need at least 2 other ones because you have to fit this other guy. That's the problem.
Yeah. But I mean, with all this data, you can make such a fit.
No, because that is the current insertion time.
That's right.
So you need. So if I have 2 parameters, I'm just saying.
I
if have
see.
2 parameters,
Sorry. I don't know.
I think that in order to do that, we need to go to smaller source separation to see the effect. If we go to larger source separation, I don't know if the signal to noise would allow that somehow. But
This data is
but-
pretty clean.
yeah.
So I wouldn't, you could try, I mean, you have a smaller one too, right? You did, yeah.
Yeah. Actually, I want to try to use Emanuele's expressions and see if I can get an estimate if this sourcing separation, how good is it? But yeah, I haven't tried it yet.
Because if you really want to be peaky, there is a curvature in the distance. It's not that flat that you say everything.
No,
Just to be peaky.
I've seen worse plateaus than this, but
But maybe you can move, you can take some, just, okay, here, just check it. Take some spline fit, so just completely agnostic fit, and then take numerical derivative. And then when you see 0, then you are very, very happy that that's
yeah. No, I think we should do the excited state analysis, but yeah, for this presentation, I think that's fine.
now that was very fair.
And it is a heavy final mass, so
It's a heavy pioneer.
the old GA results of heavy final mass, this was.
Yeah, actually, didn't we check like yesterday if the effect on oh yeah, the expression. Okay. More questions and comments from Zoom? No?
From me.
Yeah. Yeah, please go ahead. Can you hear us?
Yeah,
Please go
sorry,
ahead.
I cut off the first word. It was not from me.
Oh, okay.
So so the current that you use is what you showed. So with the wrong factor or?
So the current you use in the calculation at the 2/3 for the down quark, or was the correct one? Just to be sure. You use the right one? Okay.
But because we had the code. I mean, this is an old code that we wrote some time ago. So yeah.
So just to be sure.
Yeah.
Otherwise,
But we will double check. Yeah, we'll double check.
Just by curiosity, I mean, how do you,
which action do you use to flow? Wilson. Wilson action, okay.
Yeah, that was another promise of another part of the program.
Okay.
That we should implement it second flow, but
Okay. And these could probably make some difference in the. These will make some difference in the topological chart, I guess.
well, I don't know. I think the more difference to the spectral projectors will make any.
Oh yeah, absolutely.
We have a code to the second flow. What is? We have to sort of integrate it.
No, I was asking just by curiosity.
No, it's a good point. We want to try. So the plan was to try both discretization of the gradient flow and the spectral projector, so to actually make absolutely sure and have a robust continuum.
Okay.
That's the first step. But we are generating gauges, and then we are calculating a difficult circle. So it takes a
Yeah.
little bit of time.
Okay. No.
You also flow the vector current, or just
No. That's the
only check?
Okay.
when you flow the vector current to get different ordering.
The vector current is not concerned anymore. Because
Okay. So could follow.
it runs. Actually runs. But you calculate, but that vector current is also not conserved because it's local, even at zero flow time, but it doesn't run. But you have to calculate the normalization. It can show that big. Yeah. So we use the word entity to determine ZB, and that's the bare coupling dependence of the ZV. Yeah. And it's constrained to go to one loop perturbation theory. But indeed, we use the values of the V which are determined. So we don't use the fit formula on the right side. This is just for illustrative purpose. Yeah. More questions? Okay, thanks a lot.